Hello again, my dear students, and welcome to this third part with our output stage and power amplifiers in chapter 1 for electronic free course, ECE. If you remember in the previous lecture, we have demonstrated together the concept of a class B power amplifier. In a class B power amplifier, we have observed the trade-off between having a high efficient outstage power amplifier with respect to what presented in class A. As in class A, we got an efficiency maximum of 25%, while in class B, we reach an efficiency of 78.5%. However, due to the configuration of the class B, a dead band occurs when both transistors are turned off, as you can see. So this opens a problem related to the distortion that can occur in your output voltage with respect to the input, as due to the discontinuity in the signal crossing zero. As a modified step, we propose some alternative toward getting read out of this deadband. One of these alternatives is by using what's called an op-amp or a differential amplifier driven class B power amplifier. Also, we suggest another topology toward avoiding the mismatching in the supply, in the VCC and negative VCC, through using what's called a single supply operator. Now, again, toward having or toward combining the benefits of both class A and class B power amplifier. A class A B power amplifier is product. A very early and simple configuration for a class AB is demonstrated. As you can see, my dear students, the concept here is simply you bypass the dead band region by simply inserting two batteries, as you can see. Each of these two batteries will bias up or bias down your voltage to ensure that your transistor is working. So, for example, if the input voltage is zero here, which is the central point of our dead band, what will be inputted to your transistor is not zero. Simply, what will be inputted here is VBB over 2, which makes this QN turn on. And similarly downward, what will be inputted here is negative VBB over 2, which makes this transistor again turn on. So instead of having two transistors up in the center of the dead band at zero input voltage, now your two transistors will be turned on, as you can see. And this is a very efficient way of bypassing or overcoming the dead band rule. In order to turn this into equation, we will simply deal with this as a p-n junction. Here we have the base emitter junction, and here we have an emitter base junction, because simply this is an NBN transistor, and this is a BNB transistor. So once you put a full bias voltage here or there, you make your p-n junction turn it on, and then you can write this simple equation representing current flowing in a bias. A current flowing in a bias is equals to the saturation current exponential to the voltage over VT. Now your applied voltage is VBB over 2. That's why you have this VBB over 2 multiplied by this V terminal. And this will be simply the current flowing in your p-n junction, either here or there, as both of these p-n junctions are now forward biased. On the other hand, you can consider that your VBB over 2, or your VBB in general, which is the potential differential, let me now use the plan. So your total potential here is simply the summation of the VEP here and the VBE here, and the VEB here. As you can see this equation. So VBE for the N transistor plus VEB for the P transistor will result with your VBB. Or in other words, if you turn this into current using just multiplying this equation by line here and there, the first equation, or multiplying this first equation by line both sides, then you get that VT ln IN over IS, this represents this one, plus VT ln IP over IS, this represents this one, equal to VT ln IQ over IS, which is simply subtracted from the above equation by just putting VBB in one side and other terms in the other side, and of course, first multiplying by lambda. Using this equation, you will reach this very interesting equation, which mentioned this. Sorry. Okay, very sorry. Now back to the lecture. Very sorry for this. Okay, so now this equation. Okay, this is a very interesting equation. It mentions that IN, or the current flowing in the QN transistor, this one, times IP, which is the current flowing in the P transistor, equals to IQ squared. Remember that this IQ is function of VBB over Q. So simply it's a constant. As far as you insert a certain battery to the system, this IQ will remain constant over the experiment, which means that IN times IP equals to constant. This is a very famous mathematical formula, which leads that whenever you have two variables multiplied, or whenever you have a multiplication of the two variables equals to constant, that means that once any of these two variables increase, the second variable will automatically decrease to maintain a multiplication equals to constant. What happens is typically like that. When you have a higher IN, I mean the IN is going here. When the current flowing in the loop is due to IN, that means this IP is going to decrease to maintain that IN times IP is constant. And vice versa. When the current flowing in the loop is due to the IP, the current flowing to the IN is going to be reduced, as mainly the contribution is coming from that transistor in the bottom. So what you are doing now is that you divide your region of operation into 3 regions of operation. Now let me make it like that. So I will just use another pen. Yes. So we have now 3 regions of operation. The region of operation on the extreme right and on the extreme left are typically the same as in class B. So in the extreme right case, you are working mainly due to Q1. And in the extreme left case, you are working mainly due to Q2. However, in the region in between, where in class B you have a dead band, this region, where in class B you have a dead band, now your 2 transistors are working in this region simply due to this added battery. So what will happen is, in the central point in the origin, both transistors will have the same contribution to the current. When you go to the positive side, the current due to IN increase and the current due to IP increase till you reach the boundaries here in this point where QN turns or sorry, QP turns totally off, and your operation is mainly due to Q. And vice versa will happen here in this point. So in this region, in the negative region, QP is getting more current, QN is getting less current till we reach this point where QN totally turns off. And the operation here will be due to QP. So this is how we manage to solve the problem we face in a class A or a class B current amplifier to have nearly the same efficiency, but with a full cycle of operation. Now, your QN will work in the whole positive cycle and some few time during the negative cycle. And your QP will run during the negative cycle and in a few portion of the positive. This is something like to make a handover between these two transistors. Okay, so this is simply what will happen for a class AB parameter. If you remember, my dear students, in an early stage of this chapter, we have recognized together that the main function of this block is to work as an output stage amplifier, which means that its output resistance should be as minimum as possible. And also, if you remember, my dear students, for class A power amplifiers, typically for those students who consider class A power amplifiers as their module project, I told you, please, when you do this schematic on cadence or multi-sum, please try to investigate the output resistance because it is the key parameter. Same applies here. We have to investigate the output resistance of a class B or a class B amplifier. It is goes without saying that the output resistance. So, as you can see, the output resistance seen by a class AB amplifier is typically the same as the output resistance seen by a class B amplifier. That's why we can merge this calculation once for both. Here, the output resistance can be analyzed in terms of what we can call a small circuit resistance. If you remember from your electronics 1 or electronics 2 classes, which are R small e, or the output resistance. So what you see here is simply REN paired with REP, because as you know, when we do an output resistance analysis, we deactivate all supplies. That's why you can see a ground here and a ground there. And simply you can see that the output resistance here, you have one resistance here and another resistance here. So these two resistors simply are seen parallel to each other as both the top and the bottom supply are deactivated. And that's why we have this. If you remember, my dear students, this output resistance were equals to VT, or the thermal voltage, over IN, which is the current flowing in the junction, and similarly VT over IP. And similarly, you can get that VT IPO plus IN. So you can understand from this equivalent resistance, output resistance, that the higher the current, the lower the resistance flowing. And herein, as we are considering a high power amplifier, we are considering a relatively high power, high current. That's why we consider a low output resistance. This is simply how we can consider the output resistance in a class AB or a class B output stage power amplifier. Now, let's turn to this consideration, or this circuit maybe solve the process of having that band in the central point of output signal coming from an output stage power amplifier. But in this topology, we make a very important assumption that we can build such a power supply, a DC power supply here and there, and connect them in this direction. First, you consider that you have, or it's easy to implement this supply, and it should be symmetric. Second, you don't have any possibility to tune this voltage. The voltage here between these two points is the base-to-base voltage, that's why we call it VBB. This VBB will be kept constant all the time. It's not controllable. So first, you assume a symmetry or a match between these two points. Second, you don't have the privilege of controlling it. So how we can solve these two aspects? I mean, it's always not applicable to have a super matched supply. What about mismatches? And what about if we need to vary the variation between these two bases? What will happen, or how we can manage such aspects? In this topology, we suggest another configuration. As you can see, my dear students, this portion is always kept the same, which is the base of a class B power amplifier. We are just modifying the portion to the left, which controlling the base to base. What we are doing here, my dear students, is as follows. We conduct a current here. We are flowing, there is a current flowing here into that. As you can simply know that this beta is very high, so we can assume that the current flowing in the base is minimum. So you can simply assume that this I bias will totally flow in the diode. Accordingly, this diode number 1 and diode number 2 will be forward bias. If you remember, my dear students, early in electronics 1, when we study a forward bias diode, we say that a forward bias diode is an equivalent to what's called a voltage source, if you remember. So as if you have two voltage sources in series, each with the building potential, which is, let's say, 0.7 or something like that. So, simply speaking, by putting these two diodes in a forward bias, that means that you make this voltage, a base-to-base voltage, equals 2 times the V node of each diode. So, here, you don't have any problem with symmetry. What you did simply is you put one base to that directly to the input, and the other base, which is this one, is biased or is shifted by 2 V nodes with respect to the central or the first base or the QB base. So when the input equals to 0 here, this point will be typically equals to 1.4. Because the voltage here is higher than the voltage here by 2 V. Even when the voltage here, or when the voltage in the input is negative 0.7, still this point voltage is 0.5. So again, you solve the problem of having that band by inserting these two diodes, which will create a base-to-base voltage equals to 2 V. So you don't have the problem of that band again. However, in this circuit, we have considered only one thing, which related to the mismatching between the supplies. But still, the base-to-base voltage here is constant, equal to 2 V. So we don't have the privilege to tune this. Accordingly, another circuit is suggested in this direction, which is this one. In this circuit, my dear students, still, as you can see, the portion to the right is typically the same. No change in the class B power amplifier. You are just change the circuit between the both bases, as you can see. So in this case, what will happen simply is as follows. Okay, so let me do another. Okay, so what will happen? Here we have a current source. Again, assuming a high beta, so this current source will go, and then it will be branched. Some current will be flowing into the transistor, and another current will be flowing here. We call this current IR, as you can see. This is the current flowing in the resistor. So, simply speaking, the VBB voltage here, or the voltage between the both bases, it equals to the current flowing in the resistance, which is IR, plus R1 plus R2. Again, we assume a very low beta current, so we assume that R1 and R2 are all series resistance. Accordingly, you can say that VBB equals RIR times R1 plus R2, which is typically the current flowing here. Now, let's check another point. So, let's go to another point here related to the same circuit. Let's examine the voltage drop here, which is typically a VPE voltage. And as you can see, this VPE is equal to the voltage drop on R2, as you can see. Sorry, on R1, I'm sorry. So the voltage drop VPE equals to the voltage drop on R1. Both are parallel, as you see. So simply you can say that the current flowing here is equal to VPE 1 over R1. So you can substitute this IR by VPE over 1 for transistor 1 over R1. And as you can see, if you multiply this R1 in the bracket, you will get this. That VBB equals to VPE1 times 1 plus R2 over. Now you have two advantages. The first advantage is you have avoid the mismatching between supplies. You don't have supplies anymore. You create this base-to-base voltage using a transistor, two resistance, and a current source. So this is the first advantage. A second advantage is your VBB voltage, your base-to-base voltage, is now an adjustable voltage. So you can adjust R2 and R1, or you can simply make R2 a variable resistance to tune the base-to-base voltage here. Then you can control the base-to-base voltage. That's why we call this as a VPE multiplier. Simply, you multiply VPE by a factor, which is 1 plus R2 over R1, and you have the opportunity to select the appropriate factor to multiply VPE. That's the advantage of using this circuit with a transistor, a two resistance, and a current. If you remember, my dear students, from the beginning of this lecture, we have considered that power amplifiers are commonly implemented using bipolar junction systems. However, principally, you can implement the same concept of circuit using MOSFET. And one of the examples where you can use MOSFET is this example. I will try to use the same concept of describing the out-of-stage power amplifier by using this MOSFET. So referring back to the same concept, as you can see, my dear students, we have the same structure here, but using a MOSFET instead of using a bishop. As you can see, we have a N-channel MOSFET and a P-channel MOSFET. If you remember from your current classes, you can revisit the lecture recorded over YouTube, that this transistor turns on when the VGS is equal to or greater than the threshold. And then this transistor turned on when this VSG is equal to V threshold or greater. So it is typically the same concept as we do in our VGT model. And again, instead of having what we call a base-to-base voltage, here we have what we call a gate-to-gate voltage. Now, the portion to the right, sorry, to the left, is responsible to control the gate-to-gate voltage. As you can see, we have a current source driving two transistors. What is interesting, what is unique in these two transistors is that your gate and your drain are connected or are short circuit. And this is a very common configuration in a MOSFET when you would like to force your MOSFET to work in the saturation region. Again, please revisit the electronics lecture in order to remember this saturation and triad configuration. So when VDS is greater than VGS minus V threshold is a saturation, which is the case here because VDS and VGS are equal by this short circuit. So simply, you create your VGG now using this schematic or Jesus branch. The current flow, you know that there is no current flowing in the gate. So simply in this branch and in this branch, similarly here, no current flowing. So the I bias will move in Q1 and then in Q2. That leads to the I bias equals to ID1, or the current flowing to the drain, or the current flowing in the drain of the first transistor, which is again, we are now in a saturation region, so it's Kn dash over 2, W over L, VGS minus V threshold over square. I think you remember this equation from your electronics one, right? Similarly speaking, the same I bias is flowing in here too. So this current ID2 equals to I bias equals to Kn dash over 2 W over L2 VG, now VSG, because this is a prime and V threshold absolute square. So as you can see that our VGG is simply a VGS and VSG. So you can reach this equation that VGG, which is the gate-to-gate voltage to be controlled, is equals to VGS, the voltage in the first transistor Q1, plus VSG, the voltage in the second transistor, which equals to this big equation. What is interesting here is that, of course, these thresholds and this material parameter will be kept constant all over your experiment. But you still have the ability to tune the VGG by tuning simply the I bias. So by varying the I bias, you vary this voltage, which leads to a variation in the VGG, which is typically the same like when we say a VDE multiplier. So you control the gate-to-gate voltage. So now you control the gate-to-gate voltage by varying the I bias here. And this is another configuration. So it's not widely spread to use a MOSFET in a power amplifier, as I mentioned. However, it is relatively considerable to build your power amplifier using a MOSFET. That's why I demonstrate to you this. Now we terminated together chapter 1 under the name of out-of-stage power amplifier. In the next chapter, inshallah, we are going to start a new journey with analog filter design. Thank you very much and see you with the next